And we can hear you. Okay, yeah. So
Okay,
the second
perfect.
presentation now will be given by Lutz Oettershagen about the higher order temporal age index for evolving networks. Lutz, please go ahead.
Thank you for the introduction. Yeah, my name is Lutz Oettershagen. I'm since recently a lecturer at the University of Liverpool. And this is a joint work with Niels Krieger from the University of Vienna and Peter Mutze at the University of Bonn. So the title of my talk is a higher order temporal age index for evolving networks. And this talk is based on a paper that was presented last year at KDD. So let me give you some background on the age index, which was proposed for measuring the productivity and impact of scientists by J.E. Hirsch in 2005. And he defines it as the maximum value of age, such that the author has published at least 8 papers that have each been cited at least 8 times. So we know this, we all use this all the time to rank each other. But it has also been used as a centrality measure for ranking nodes according to their ability to spread information in static networks. And one of these works is by Liu et al. And he first formalizes this notion of the age index as this function h, where m is a set of finite multisets of integers, and h maps this to an integer or elements of m. So it returns for a finite multiset of integers s, the maximum integer I, such that at least I elements j and s, where j is at least as large as I. And using this function, they define the nth order age index for static graphs. So the nth order age index SU with the order of n of a node U in a static graph with nodes V and edges E is defined as follows. The base case for n equals 0 is just the degree of the node. And then the nth order age index of this node U is defined as applying this function h to a multiset which is defined as follows. The multiset contains for each neighbor the n minus 1's nth order age index. And by this definition, they say, okay, the first order age index is the age index of the vertex U. So if we want to use this as a centrality measure for the ability of the nodes to spread information in the network, then the problem is that this definition only considers static structure of the network. Only it's defined for static graphs. However, many networks change over time, and very prominent examples are social and online communication networks. Especially communication networks like email networks or chat messages, they are highly dynamic networks. And the important thing is that the information spreads over time and not instantaneously. So we think the age index should take these dynamics of these networks into account. And to this end, we introduce the nth order temporal age index. We can use it for 2 things. The first one is we answer questions which nodes are important or central in terms of how strong is the influence of nodes over the other nodes in the network. And then we can rank the nodes. And furthermore, it leads to a core-like decomposition where we're able to find strongly connected subgraphs or communities in these networks. So we use the following network model for temporal graphs. So a temporal graph is a set of, or a pair of a set of nodes and a set of temporal edges, where these nodes are static and don't change over time. And we have a set of temporal edges, which are consisting out of 4 elements: a start node, end node, a timestamp when the edge is available, and lambda is a transition time that equals the time required to traverse the edge. For example, in this picture here, you have the node names on the left. So we have the nodes A, B, C, D, and E. And then we have the time steps 1 to 7. And we have, for example, one temporal edge starting at node A at time 1, and it arrives at time 2 at node B. So for this network, the traversal time would be, or transition time, lambda equals 1 for all edges. So the question is now, what is a useful adaptation of the nth order H-index for temporal networks? Our goal is to rank the nodes according to their ability to influence other nodes and the ability to spread information in the network. So the information usually spreads along temporal walks, and they are defined as a sequence of temporal edges, such that consecutive edges share a common node, and the timestamps of the temporal edges are increasing. So here you see as example 2 walks from A to D on the left and on the right. And on the left, we wouldn't consider this as a temporal walk because the timestamps of the temporal edges are not strictly increasing. Where on the right, the timestamps are strictly increasing. Now, for defining the nth order temporal H-index, we first define the temporal neighborhood at a vertex, depending on a timestamp. So we define the multiset n at the node Vt, which contains all pairs of nodes and times w, tw, such that there is a temporal edge from V to W, leaving at time t prime not earlier than t, and arriving at time tw. You see the schematic here, which captures this definition. We have this node V and the node W, and this temporal edge that exists at time t prime, which is not earlier than this time t. And our arrival time at the vertex W is tw equals t prime plus lambda. Now, using the temporal neighborhood, we define the nth order temporal H-index. So the nth order temporal H-index of a node V is defined as this term, where we now have for the nth order temporal H-index, the order n, we have the node and the timestamp. We then apply, we have a similar recursive definition as in the static case. So we apply this function h on the multiset, where this multiset contains for each pair w, tw that we have in the temporal neighborhood of the node V at time t, the corresponding n-1th order temporal H-index. And as base case for n equals 0, we define the value to be the size of the temporal neighborhood at the node V at time t. And this notion captures the node importance in terms of temporal reachability. So nodes that have a high reachability, especially to nodes with also high reachability, will be ranked high. So we will take a look at some example. Where we now have a temporal graph where the transition time lambda is equal to 1 for all edges. And we construct a reachability tree that captures for the node F, for which we want to compute first the first order temporal H-index, which captures the outgoing temporal walks from F. And in this reachability tree, we have always in the node of the tree, the node where we are in the temporal graph, and the arrival time where the temporal walk arrives. Where for the root, we just start with time 0. So for example, for depth 1, we have now, we we can start a temporal walk going to node D. In our temporal graph, we arrive there at time 2 because, okay, this temporal edge exists at timestamp 1 and we have a duration of 1. So our arrival time at D is 2. So we add this node in our reachability tree. And we do this similarly for the node E, H, and G. And for computing the temporal H index, we now can compute for these nodes the neighborhood size, which corresponds to the temporal walks or the extension of the reachability to depth 2. So we then see, okay, this node D2 in our reachability tree has 3 neighbors. And this is the temporal neighborhood size for this node here. And this corresponds to the 0th order temporal H index at this position. And we have similar values now for E2 and so on. Then the first order temporal H index value of the node F would be 3 because we have 3 values larger or equal to 3 in this set, in this multi-set. Okay, now we can do this similarly for the second order temporal H index, where we just have a 1 step deeper reachability tree. We can evaluate this and then we see at the end, okay, this value is 1. So taking a look at this tree, we see that for if we have an nth order temporal H index of k, which is larger than 1, there are at least k to the power n plus 2 minus k over k minus 1 descendants of this node u, the descendants u of the root in our tree that have depths at most n. So this means we have some lower bound of temporal walks outgoing from this node for which we have a temporal nth order H index of at least k. On the other hand, if we choose our n very large, or if we choose it large enough, the nth order temporal H index goes converges to 0 for all values of n that are larger than the maximum temporal walk length. And the reason is that obviously, like the length of temporal walks in this finite temporal graph is finite. And then if we choose too deep, then the value will be, we will always have 0 neighbors in our reachability tree. Okay, so far, what have we seen? We adapted the nth order H index for temporal networks, and we can use it to rank nodes to their spreading capabilities, as we will see later. So what's next? The static nth order H index has this property that it converges to the core number of the vertex u for increasing values of n. And what's the core number? It's based on the k-core. And a k-core is a maximum subgraph gk of g, such that every node in gk has at least k neighbors in gk. And then node u has a core number of k if u belongs to a k-core, but not to the k plus 1 core. Here in the corner, you see the graph that we use for this example, and there's the static k-core highlighted. So this is independent of the timestamps. It's just on the aggregated or the underlying graph. If we take these 5 nodes, the induced subgraph, each node has a degree of at least 3. So, and then we can define a similar decomposition for the temporal variant of the nth order H index. However, we need to adapt this definition slightly. So we define the temporal nk pseudocore. and let k and n be integers, then the temporal nk pseudocore G is a maximal induced temporal subgraph, such that for all nodes in the subgraph, the nth order temporal H index is at least k with respect to the original graph or temporal graph G. So NK pseudocore is a temporal subgraph containing nodes with similar temporal activity and importance in the network. You see an example here on the right. So in red is still the static 3 core, and then we have two NK pseudocores. The one is for both are for n equals 2 and for k equals 0. Okay, it obviously contains a complete graph because the H index is at least 0. And then we have for k equals 1, we have this gray background and green the set highlighted with the gray background and the green line. So this decomposition also leads in some hierarchical decomposition similar to the K-core. However, for a node V in our NK pseudocore, the inequality that the nth order H index is at least k does not hold in general with respect to the pseudocore. That's why it's called pseudocore and not core. So it only holds with respect to the original temporal graph. Okay, for the computation, we introduced two algorithms. We can apply the rather naive recursive algorithm, just applying this definition of the nth order temporal H index, but this is not very scalable. So we introduced another a streaming algorithm that uses a single pass over the edges in reverse chronological order. It computes for each node the ith order H index for all values of I between 0 and n. And this is different for the recursive variant where it just computes the results for one specific value of n. And here you see a comparison of the running time, and we see that the recursive variant has some quadratic term in the maximum degree of the network. One disadvantage of the streaming variant is that the edge transition times, so the lambdas, have to be uniform, where in the case of the recursive algorithm, they can be for each edge or temporal edge different values of lambda. So the basic idea of the streaming algorithm is as follows. We use we stream over the edges in reverse chronological order. So we start with the latest time steps and go backwards in time. And if we have two edges with equal time steps, we just process them in arbitrary order. Then the algorithm manages for each node and each value I between 1 and n, a multiset of the H indices obtained from the neighbors. And when an edge is processed, a temporal edge is processed, we update the size of the temporal neighborhood, which is always increasing for the decreasing value of t. And then in the second step, we append at u the I+1's order H index of the multisets of the ith order H indices of at the node V. So this holds for an edge from U to V at time t. And after processing all edges, we return the ith order indices obtained from the multisets managed at each node. So we run some experiments on various data sets. We use data sets from different domains, communication networks, social networks, and human contact networks. And the size varies from 2,000 nodes to around 2 million nodes and 60,000 edges to around 40 million edges. So first we compare the running times between the recursive variant and the streaming algorithm. And first take a look at the value for n equals 8. And we see that we have speedups of up to 2 orders of magnitude using the streaming algorithm. And this also holds for higher values of n. Okay. Then our second experiment is we want to compare the pseudo-core decomposition to other k-core decompositions for graphs and temporal graphs. And first we define this indicator function R that is 1 if the node U has a temporal walk to the node V and otherwise 0. And then we define 2 kinds of reachability scores, a global variant and a local variant. So given a pseudo-core or a k-core G and K, where over the set V prime and E prime, then the global score is the normalized ratio of nodes that from inside the core can reach nodes outside of the core. And the local score is the reachability normalized inside the pseudo core. And we compare this for values of n equals 8 and n equals 16 to the conventional static k-core computed on the aggregated underlying graph and the kh core by Wu et al. For h equals 4 and equals 8. So here you see the results. A higher value is what we are looking for. And on the left is the global variant and on the right, the local variant. On the x-axis are the core numbers, but the high-ranked cores or higher core numbers are on the left, and then low-rank core numbers go to the right. And we see that our pseudo-core definition captures these communities or these groups of nodes that have a high reachability in the group itself and in the graph itself much better than the baselines. Okay, and finally we applied our centrality measure as in a use case of identifying influential spreaders. So to this end, we first computed the mean node influence for each node and for different infection probabilities using independent SIR simulations. So these SIR simulations are susceptible infectious recovered simulations. At the beginning, all nodes but one are susceptible and one node is infected. And then we have some model this spreading process in this network for the infection probability beta. And at the end, we count the number of infected nodes and recovered nodes. And we rank the nodes according to their ability to spread, or if we start at this node, how much the spread goes through the network. This way we obtain this SIR rankings, and we compare these rankings then obtained by different centrality measures using Kendall-Tau B rank correlation. So a higher correlation between the ranking of the centrality measure and the ranking by the SIR simulation means that the centrality measure captures better the ability of the nodes to spread information or spread disease in the network. So we compare the temporal H index for value for n equals 32 and n equals 64 to a set of other state-of-the-art centrality measures for this task. At least most of them state-of-the-art, so the degree centrality, static H index, Then also the static K-core, the temporal closeness, which has been shown to be very useful for this task, temporal walk centrality, gravity centrality, local gravity centrality, and Cornus plus. And here you see the results for 3 data sets. The first one is the human contact networks, and the other one are communication networks. And especially for the communication networks, you see that the correlation for using the temporal, the nth order temporal H index has strongly higher correlation compared to the baselines. In case of the human contact networks, the temporal closeness is better in a few cases or for a few values of beta. Okay, in conclusion, we introduced or we adapted the nth order temporal H index, and we obtained 2 variants. So in this talk, I focus mainly on the outward variant, which uses the incoming temporal walks. However, we can symmetrically define an inward variant, which uses incoming temporal walks at each node. And this way, we can rank the nodes by their ability to obtain information in the network. We introduced also a highly scalable streaming algorithm and showed that the pseudo-core decomposition as we defined it is effective if we want to obtain groups of nodes that have a high reachability scores. Finally, we showed that the nth order temporal H index can be a successful heuristic for identifying possible superspreaders in temporal networks. So you can use this QR link to obtain the paper, the archive version of this paper. Thank you.
Okay, thank you. We have time for 1 or 2 questions. Are there any questions from the online participants or the offline?
Yeah, I have one. And so you were talking about the correlation between your measures and SIR spreading success. And you said that for the Malawi data set, it was not as successful as for the communications data sets. Is that right?
Yes. So it is not as strong. So it is successful, but I can.
Not as strong as, for example,
yes.
Sometimes.
Yes. Yeah.
So if I remember correctly, the Malawi data set is like a person-to-person RFID tracker in a village, right? It's like
yes.
89
yes.
people. Which I think will be a little bit more like the degree distribution will be a little bit even. There's some assortativity, that kind of thing. Whereas the 2 communication networks will be like very power law, I guess.
Yes.
Is that true? And do you think that's important here?
Yes, I think so. This is this might be the reason. Yes.
Okay. So then I guess does that tell us much about like some sort of graph structural characterizations for when this is a really good predictor versus not?
Sorry, I
was wondering if you could comment on what characteristics of a graph mean that this particular metric is a useful one for disease control.
Okay, yeah, so this might be indicative for this, but one thing to take or keep in mind is that this is just some, like it's a heuristic approach. I'm not sure that this is some general rule that we could conclude from the data set that we run this on, that this is like some general pattern that we would observe. Like, I'm not sure. This might be interesting to investigate further.
I'm certainly interested, so send me an email or I'll
okay, yeah, sure.
Cool. Thank you.
Thank you.
Okay. See no other questions. We also basically are just at the end of the time slot. So let's thank Lutz again.